Okay, we have a problem here. Example T does 8. The solution is not quite different from the other examples I just gave you. So we have an MC section, which is a miscellaneous channel. Okay, so this is simply a miscellaneous section. Uh, okay, and it is placed on this manner so as to form what you call a box shape section, which later will be tied by plates to see to it that it will act as a unit in terms of the serviceability requirement for slenderness. Okay, so the procedure is just the same. We get your AG on the basis of the gross requirement, the yielding. So this is for the yielding requirement, and this is for the fracture requirement. Okay, so this you just equate whatever is your TU is given. Okay, so directly given na yung TU natin. This is 490 for the both of the channels, so you divide it by 2 in order to get 245 per channel. Okay, and then we get the net area, but the net area is equal to the effective area simply because your section is connected on all elements on all sides, therefore your u is equal to 1. Okay, so this is the rather part that may not be very comfortable to you as beginners, so you need experience to get a good ratio of the flange thickness and the web thickness. Remember, class, that if you have a channel section, always the flange thickness is greater than the web thickness, including W shapes and S shapes. Okay, so this is always greater than W. So based on your experience, you can come up with a good approximation of what the thickness is of the flange and the web to compute for the uh, net area on the basis of the requirement for AE. Okay, so AE is equal to AN on this particular. Okay, remember that A uh, N or is equal to AE, so this is equal simply to AG minus, since is a straight pattern, so this is simply the diameter of the hole multiplied by the thickness. Okay, so that's your formula here. So this is now, we have how many holes on the flange? Okay, so ilan yung holes natin do sa flange? We have 1, 2 holes. Okay, so we have 1, 2 here. We are considering, class, we are considering only one channel always, because we use a half value of your TU. So take note that we consider only one channel. So you have 2 holes on the flange and also 2 holes on the web. Okay, so that's why you have a 2 here and a 2 there. Then you have here a diameter, and the thickness. You can make use of trial and error in case you don't have any experience to do it. And then basically you can solve now for AG2 requirement on the basis of this formula. So AG2 becomes 6.63, which is greater than AG1, which is 5.44. So this is your target area for your design. Okay, so you proceed now with the required serviceability limit of R minimum equivalent to L over 300. Okay, so this is now 30 feet times 12 divided by 300. You have 1.2 inch as your minimum radius of gyration for the built-up section. So you are considering here the built-up section. So for the R minimum of the actual, it must be at least greater to or equal to 1.2. And of course, looking into the table again, so this is now a table reference. Looking into the area greater, this must be greater than AG2 requirement. Okay, yung nakuha natin kanina, which is 6.63. So greater, and then your TW is near your assumed value. So these are the assumed. And of course, your Rx must be greater than 1.2. So where is your Rx? This is your minimum, okay? Rx. And your Ry is here. Okay, Rx can be directly uh, taken from table, but Ry must be computed on the basis of a theorem. Okay, so you have compute this on the basis of the value R. Yy is equal to the square root of I over A. Okay, Iyy over A. Okay, so this is directly from the table, but this is not directly from the table. I did not show the computation, but Ryy here will be greater than Rx. So you use the minimum value, which is 3.87. So check the capacity of this by simply uh, getting the exact value of your A effective on this basis using the actual AG del, and then just substituting the actual values of T, F, and TW del, you get your actual effective area. And then try to check it, and it must be greater than 490. Okay, so the value 2 here is for 2 channels, no? Kasi 1 channel lang ito, so ito for 2 channels. And that will be compared on the total value of 490, not on the 245. Okay, so this is safe. So that concludes your solution on the strength requirement. Now, for the additional design on type plates, this is just a provision, a code provision on the determination of how big and how thick the type plate is. And a type plate is simply a requirement to make your independent section behave as a single unit. So you place it somewhere at the ends and somewhere at the middle, no? So to get the spacing, you have to check for the maximum length. So this is the L, okay? On the basis of your slenderness ratio, okay? So we know that L is 300R. This was obtained from L over R equals 300. Okay, so this is a serviceability uh, okay, this is a serviceability limit. Okay. Okay, so you get now your maximum R to be 25 feet, which means that all lengths, all type plates exceeding the spacing of 25 feet will give some problems on slenderness because it will act as a single value, single channel rather than a double channel. No? So you must fix your length at least 25 feet or less. So the easiest way is to divide the total length of 30 into 2, okay? Para hindi ka na mahirapan, hatiin mo na lang sa dalawa. So these are what you call now your tie plates, okay? So how to get the length of the tie plate and the thickness of the tie plate, you just apply the recommended limitations of LRFD D2 P16.1-24. So this is now your formula for the length of the tie plate. Okay, so the length of the tie plate must be greater than, okay, LT. Let's make it an LT there. LT must be at least greater or equal to 2/3 the distance between the connection. Okay, so this is the C. So the distance between connection is actually from this bolt here up to bolt there, which is approximated maybe by the end-to-end spacing of your miscellaneous channel. Okay, so this is actually 10 inches in our figure there. So you just substitute there, L is equal to 2/3 of 10. So this is around 6.7 inches. Okay, it was rounded into 8 inch to give you a better value to accommodate what the holes of the rivets or the bolts there, but it must not exceed 10 inch for practical reasons. Okay, for the thickness of the tie plate, you just make use of this again as the formula. So thickness of the tie plate is equal to 1/50 of the distance, which is I'm going to use now the actual distance of 8 uh, sorry, yes, 8 inches, or the length of the tie plate. So I'll be getting uh, how much? So 8 over, okay, so this is only point 16, or we can use what, for consistency, we can use this 10 here, not the length of the tie plate. No, we can use the distance between the line connection. So let us use 10. Okay, 10 for this value. So this is 1/5 or point. I think this will be point 20. Okay, so still it is very far from 1/2. So the conclusion, rounded to 1/2. So the reason for that, class, is because at least your thickness must be very near to the thickness of the member. Okay, so if you are connecting something and the connector thickness is less than the thickness of the connecting member, then there will be possibility of not, okay, not providing stiffness or stability on the connection. So better you make sure that your thickness of the member, which is was designed here on here to be, I think, 0.575 and 0.38 for the web. So you just make sure it's very close to these two. So a good choice is to use 1/2. Okay, so this is now a better choice. Anyway, these are just supplementary provisions for built-up shapes. So these are used on built-up sections. This has nothing to do with the design of lacings that are lattice and lacings that are used to stabilize columns, no, built-up columns. And ano pa lang ito, no? Tie plate for slenderness pa lang ito. To ensure that the slenderness limits are taken care of. Okay, so that's it for the example problems. I hope you are enlightened with how the analytical procedure and the design procedure is done on steel tension members. Thank you very much.